This is Unit 1, the Alphabet and Grammar of Geometry. Preview video 1.3, Geometry Grammar. Sit tall. Close your eyes. Your eyes closed. Ready? Inhale. Hold your breath. Taking a look here, you should be on this page. Get a date, time, and location. This is lesson 1.3, Inductive and Deductive Reasoning. Take a moment and just glance at these key terms. The English alphabet consists of 26 letters. The geometry alphabet consists of only 5. A point, a line, a segment, a ray, and a plane. With these 5 letters, these letters form words of geometric diagrams. An example would be 2 rays with a common endpoint. And that was one of our first words, was the word, if you will, geometric word of an angle. Today, we are going to discuss the grammar of geometry, better known as geometry logic. There's going to be key words that we're going to go over today, over the next 20 minutes. These key words are conditional, converse, inverse, contrapositive, inductive reasoning, and deductive reasoning. Conditionals, converse, inverse, contrapositive, inductive reasoning, deductive reasoning. You're going to need your reference booklet handy today. Make sure that's close by. A conditional statement is an if-then statement. It implies cause and effect. Cause and effect. All commercials, and that should be an A, advertisements. All conditionals and advertisements are conditional statements. They imply cause and effect. Here's a logo, the Walmart logo, with its slogan, save money and live better. What this logo is communicating, along with the tagline there, is if you shop at Walmart, that would be the cause, then you will save money and live better. What is the cause of this conditional statement? And it's a visual conditional statement. The cause is if you shop at Walmart. The effect is you will save on money, and therefore, that little symbol means therefore, you will live better. So all advertisements, all commercials are conditionals. In any conditional statement, the cause is called the hypothesis. The effect is called the conclusion. The hypothesis and the conclusion. Now, a conditional, which is an if-then statement or cause and effect statement, if, then, it can be modified 3 different ways. Modified, flipped around. This will make sense in just a moment. One is the converse, which means you switch the order. Inverse, you negate or say the opposite. Contrapositive, you switch and negate. Let me give you an example. Follow along. Here's a conditional statement. If it is sunny this weekend, then we will go to the beach. If it is sunny this weekend is your cause. And going to the beach is your effect. Okay? The converse means to switch. If I switch, it would read something like this. If we go to the beach, then it is sunny. Notice we took the sunny and the going to the beach and you switch it. That's converse. Inverse, you negate, which means to say the opposite of. So, sunny, beach. If it is not sunny, then we won't go to the beach. Notice we kept the order. The original order was sunny and beach, and we simply negated or said the opposite of. Contrapositive, you do both. You switch and negate. So if we don't go to the beach, then it is not sunny. Let's try another example. I'd like you to do this page where you take this conditional. If you eat an apple, then you eat a fruit. That's a conditional. Cause, eat an apple. Effect, eat a fruit. I like you to write the converse, the inverse, and the contrapositive. Do this on your own, then restart and correct. Pause the video. Okay, welcome back. I have simplified the wording and I have totally botched the grammar to simply highlight what's true. We start with if you've eaten an apple. So if you have an apple, or if apple, I'm going to shorten it that much, then you've eaten fruit. If apple, then fruit. The converse would be if fruit, then apple. You switch it around. If you've eaten a fruit, then you've eaten an apple. The inverse, you negate. If you haven't eaten an apple, or if not an apple, then you have not eaten a fruit. Contrapositive, you switch and negate. If you've not eaten a fruit, then you've not eaten an apple. Converse is switch. Inverse, negate. Contrapositive, switch and negate. Now come over here. We are going to analyze what's considered the truth statement or the truth value. So let's start with our first one. You're going to do this with me. Okay, the truth value. If you eat an apple, then you eat a fruit. Ask yourself, is that true or false? You have 5 seconds to check. That is a true statement. Yes, if you've eaten an apple, you've eaten a fruit. That's a true statement. Keep in mind, in this case, the conditional was a true statement. Let's come down here to the converse. If you eat a fruit, then you eat an apple. You have 5 seconds to determine whether or not that's an always true statement. Not a sometimes true, an always true. That would be false because there's an exception. If you eat a fruit, you could be eating a banana. And if you're eating a banana, you're not eating an apple. So the converse in this case, because it's not always true, we say false. The inverse, if you don't eat an apple, then you don't eat a fruit. You have 5 seconds to determine the truth value of that statement. That's also false. The reason is, if you don't eat an apple, well, you could be eating another type of fruit, correct? This last one, if you, is a contrapositive, the switch and negate. If you don't eat a fruit, then you don't eat an apple. You have 5 seconds to determine the truth statement there. This one's true. If you say to someone, I have not eaten a piece of fruit today, then you have not eaten an apple because an apple has qualified as a fruit. So this entire page demonstrates a really simple concept in logic training. If a conditional is true, only the contrapositive is also forced to be true. The inverse and the converse are like maybe statements. We're not sure. Now, if a statement is conditional is true and the converse, you need to change this to converse, not contrapositive. Converse. Converse are both true. If these are both true, then we would call that statement biconditional, which means it's true under both circumstances. Now we're going to talk about inductive and deductive reasoning. I'd like you to take a look at these photos very carefully. They're all golfers. And ask yourself, what do you notice about every single one of these golfers? Specifically about their clothing. What do you notice? In every situation, all the golfers are wearing a hat of some sort. Obviously, baseball cap seems to be favored, but a hat of some sort. So if you were to watch hundreds of golf matches and log the number of golfers that wear a hat, it's probably a pretty high percentage. Now imagine you knew nothing about professional golf attire. So to learn more, you decide to attend all the professional golf matches in a year, and you observe every golfer's outfit. After observing hundreds of golfers on the course, you conclude that if someone is a professional golfer, then he or she always wears a hat on the course. Notice, you come to a conditional conclusion. If someone is a professional golfer, he or she wears a hat on the course. You come to the general conclusion that all professional golfers wear hats on the course. This is an example of inductive reasoning. Inductive reasoning. You take in observations and you come to a general truth. If you're a golfer, then you wear a hat on the course. So inductive reasoning is this. Inductive reasoning you take multiple observations and you come to a general truth. That's called inductive reasoning. Now, if you take a general truth and you apply it to a specific situation, that is called deductive reasoning. Inductive, you discover truth. Deductive, you apply truth. Let me give you an example. Going back to the golf example, after multiple observations, you come to the conclusion that all professional golfers wear hats on the competitive course. Okay, this all come to the conclusion. Right here, write the word truth. You come to the general truth. This is called inductive reasoning. Just put in as a shortcut. Now let's say you meet a Mr. Tin Vu at a restaurant, and he tells you he's a professional golfer. You're at a fancy restaurant, so the guy's in a suit and a tie. He's sitting in the restaurant in a full suit and a tie. You ask yourself, what assumption can you make of his choice of clothing when he is on the golfing green? What assumption? What conclusion? And the conclusion is, Mr. Vu wears a hat while golfing. So the discovery that all golfers wear hats on the golfing green, that's called inductive reasoning. Inductive reasoning discovers truth. Taking that truth and applying it to Mr. Tin Vu, even though he's not wearing a hat at this moment, you don't see him in a hat. Wow, that's a bad hat. Oh, you artist, I need some help. Okay, that is my attempt at a baseball cap. Horrible. But anyways, even though you don't see a hat at that moment, you can deductively deductive reasoning applies a truth to a specific situation. To see if you understand this, I'd like you to read the short paragraphs and check the box whether it's inductive or deductive reasoning. Pause the video. Let's take a look here. You know all Olympic athletes must win at the national level before competing at the International Olympic. Gabby Douglas competes in the 2016 Olympics, therefore you conclude she must have won in the gymnastics. So you know that you take a truth and apply it to a specific person. That was deductive reasoning. You are testing a hypothesis that the rate of a falling item does not change depending on mass. Okay, you do hundreds of experiments and you conclude, in this case, you discover truth. That was inductive reasoning. What's important to understand is that in geometry, most of the discover truth process, the inductive reasoning process, has already been conducted and solidified over literally thousands of years. In other words, these men and women and dozens more like them have conducted experiments over and over again and came to generalized truths about geometry, including, but not limited to, of course, the most infamous or famous, depending on how you think about it, Pythagoras, Plato, Euclid, Hypatia, Brahmanputra, Khayyam. These are all geometry mathematicians from a variety of countries and centuries, and they all have discovered truth. All of that was the heavy lifting of inductive reasoning. In geometry, therefore, we're taking these discovered truths and applying it. In geometry, the discovered truths that we are using are called definitions, properties, postulates, theorems. Definitions, properties, postulates, and theorems. Those are all discovered truths that we will apply in deductive reasoning. I need you to go to your reference booklet, please, and find these 2 pages in your Unit 1 section. They're called Algebraia Properties. In other words, we are going to be summarizing truth that you already know, but we're going to do it specifically with algebra because you're at this moment more familiar with algebra than you are geometry. So go to your reference booklet in geometry, Unit 1. There's your first section. Find this page, Algebraic Properties. I'll wait 10 seconds. So what we're going to do is we're going to summarize some of the algebraic truths that you already know. Distributive property. If you add or subtract on one side of the equal sign, you know it is collect-like terms here. We call that addition and subtraction of real numbers. If you're again on one side of the equal sign only, and you multiply and or divide like this. I'm multiplying and dividing, but I'm on one side of an equal sign. That's called multiplication and division of real numbers. Both sides. Notice I'm going to be working on both sides now. If I do this, if I want to solve for x here, and I go plus 2, I end up with 5x equals 10. By adding plus 2 to both sides, that's called the addition property. We add the word property when you're working across the equal sign. Multiplication and division property, again, you're multiplying or dividing on both sides of the equal sign. For example, 1/4 x equals 10 times both sides by 4. Over here, 6x equals 36. Divide both sides by 6. Again, you're working on both sides. Multiplication, division, property. Then you have what's called the cross multiplication property, which allows us to do this. And solve. Also allows us to do this. Always show your distributive. Do not do the distributive in your head. Then you have something called the square root property. Watch carefully. If I have x squared equals 64, the opposite of squaring is square rooting. So I'd square root. The opposite of squaring is square rooting, and I would get x equals 8. Warning. In the don't do this, watch very carefully. The opposite of squaring is not dividing by 2. And we would end up with x equals 32 there. What I just did in that don't do this symbol is incorrect, because that right there is not a 2. It means times by itself. So the opposite of squaring is not dividing by 2. The opposite of squaring is square rooting. Same thing, the opposite of square rooting is squaring. So if I have square root x equals 6, I can do this. Ta-da, you're done. Substitution property says this: if I have 3x equals something and I define x, I can substitute it. I'd like you to read this and fill this out in 10 seconds. Go. X plus x is 2x. X times x is x squared. I'd like you to go back to your preview notes now. We're right here. Now I'd like you to take 1 minute and summarize the main concepts from this lesson. 1 minute. Summarize. You're summarizing. Good job.